When nature talks about growth, it uses mathematical symbol E. Let's talk about E today. E is also called as Euler's number. There are things in nature that grow in proportion to their size. For example, cells that grow by doubling. Or if you take rabbits, they grow by reproducing. Larger the size you start with, the larger is the growth. Or if we talk about radioactive decay, where a large atom disintegrates into small, and the amount decides how much of decay that happens. So we are talking about growth that is proportional to the size and is continuous. For, ex- for example, things that double or half per unit time, and we'll talk about continuous part later. Let us take an example of a bank. Okay, let's say you put some money there and it doubles the money for you. The simple formula that is used for compounding is amount equal to principal into 1 plus rate to the power of t. Let's take a very simple use case. Let's say you put 1 rupee and the bank gives you 100% rate, which basically means R is 1, and it doubles it at the end of the year. So time period is 1. So when you put this into the formula, you will see that A equal to 1 into 1 plus 1 to the power of 1. And that becomes basically 2 rupees at the end of the year. This looks little strange. All through the year, the amount in the bank is 1, and at the end of the year, it becomes 2. If you withdraw an amount at the end of the 6 months, you get back only 1. So you convince the bank to double it every 6 months. That means there are two time periods, and the rate is half compared to annual. In this case, it becomes 50% or zero point 0.5. You see, at the end of the year, you get 2.25. What if the bank compounded it every quarter with one fourth the annual rate? It would be little more. And then what if it was compounded every month, and then every day, and then every hour, and then every second? We see that the amount at the end of the year is converging to a number, and this is approximately equal to E. Let us generalize it. Let's say you have X number of intervals, and so compounding happens X times, and the rate is divided by X. So the general formula is 1 plus 1 by X to the power of X. This is the same amount formula where we have put X as the term. Now what happens when we take this X to be really really large, or in the simple words we say that we want a limit on this where X is tending to infinity. What is this value when X tends to infinity? And that we know is E. So the E is defined as limit X tends to infinity 1 plus 1 plus 1 by X to the power of X. That is the definition of E. So that's where E comes from. If we have to generalize it a little bit, it's e to the power of z, which is equal to limit n tends to infinity 1 plus z by n to the power of n. So we were talking about e, now we are talking about e to the power of z. So that's the generalization, one more level. Now this brings us to another point, which is the continuity thing. So in this, what we are saying is that every instant in nature there is growth happening for that phenomena, and when you take this instance to be really really small, which means there are infinite number of them over a particular time period, then the growth will be equal to e. When things are doubling, but they are doubling every small instance of time, then the the growth that you will see after a time period will be e. Let us look at some other interesting properties of this function. So here we are trying to plot e to the power of x, and in the second column we have e computed for different values of x, which is in the first column. and if you see, the shape of the curve looks like this. You will see that the area under the curve at any point on this curve is approximately equal to the value of e to the power of x. So if you look at the sum on the right bottom of the Excel, you will see that it is approximately equal to the value in the second column. So this is approximate because right now we are using point 0.1 as the step, so it's not exact, but if you did integration, you will find that it will match. If you compute the slope of this curve at any point, you will see the slope is equal to the value of the y, or the height of the point on the curve. Look at the first point. The height of the point is 1, or the y value is 1, and the slope there is 1. Look at the second point. The slope is 5 and the y value is 5, or the height of the point is 5. So that's one more very interesting property of this function. If we use calculus and define this precisely, what we are saying is that dy dx of e of x, which is the slope, is equal to the y value, which is e to the power of x itself. So this is a function which differentiates or integrates to itself. You can raise e not only to real numbers, but you can raise it to complex numbers as well. So if you raise it to a complex number, e to the power of I theta, that is defined as cos theta plus I sin theta. So if you have a point in two-dimensional coordinates and you want to represent in polar coordinates, that means you want to talk about the angle that point makes. You can use this, and this takes us to the next most important and most beautiful equation, which is e to the power of I pi plus 1 equal to 0, and that again can be easily got from the previous equation, where if you ei pi becomes cos pi plus I sin pi, and sin pi is 0, cos pi is minus 1, so that basically is the formula. E to the power x, by the way, can also be computed using a series, and this is called Taylor series expansion of e to the power of x. So you can basically write e to the power of x is equal to 1 plus x square by factorial 2 plus x cube by factorial 3, and so on. The general term being x to the power of n divided by n factorial. So let's try to compute that using Google Sheets and see if it does make sense. And you can see that the first term, which can be seen as x to the power of 0, is itself 1, and it contributes 1 to the total sum. The second term also contributes 1 and makes the sum equal to 2. The third term contributes 0.5, so the sum becomes 2.5, and if you go and if you start adding more and more terms, you will see you will start getting closer to the actual number. Here, because of computations and rounding off, we are seeing zeros, but you will get smaller and smaller numbers, and you will get to the actual value. E also appears at other places. For example, if you know some basic stats, you will know that there is a normal curve which is used to represent metrics in real worlds. For example, if you take heights of people and you plot them, you will see that most of the people will have a median height or a height in the center, but and people with very small height and very large height will be far lesser, and everything will be more concentrated in the center, and it will form a bell curve, and this bell curve is used in many places. And if you look at the formula of bell curve, you will see that there is a E that appears in that bell curve. So nature has used E at many places, and probably we still have to find out the complete connection, but we see that nature, when it talks about growth and natural things, it does use E. If you have made it this far, thank you for listening, thank you for your patience, and if you know some more interesting things about E, do let me know in the comments. Thank you.